Hello and welcome to part 2 of the AI Fundamentals course, Document Intelligence and Knowledge Mining with Azure AI Search. My name is Andrew Conniff and I'm a Microsoft Technical Trainer or MTT at Microsoft. This session is about working with documents. And documents represent data in different formats, usually different locations like SharePoint, OneDrive, and other document stores. It represents incoming data in forms of invoices, contracts, and receipts. So let's get started. The session is in 2 parts. It's the AI Document Intelligence, what is the Azure AI Document Intelligence, and knowledge mining with Azure AI Search. So in this section, we're going to cover 3 different areas. What is AI Document Intelligence? The 3 types of AI Document Intelligence and services, and analyzing specific forms with AI Document Intelligence services. Previously called Forms Recognizer, Document Intelligence services were renamed to reflect the AI and document processing. Document Intelligence automatically reads, understands, and analyzes business documents and is made up of 3 related services. Document Analysis, which returns structured data, representations, regions of interest, and relationships, and can configure and analyze options for free or chargeable analysis. Document analysis models that were trained for specific types of forms, such as receipts, include hotel receipts, gas receipts, and IDs, invoices, that type of things. The text field names are identifiable and are available as JSON for input into the database. With custom models, you can train with as few as 5 sample forms. It does require an Azure storage, and you can customize the machine learning models for forms common in your organization. The Document Intelligence service does more than just detecting and extracting text. It uses models that understand the form fields. So for example, identifying specific types of data, such as addresses, phone numbers, dates, times, quantities, and has an understanding of the relationship between field labels and the values. So you would use Receipt Analyzer to train your own custom form extraction models based on your own scanned forms, or you can use pre-trained models to extract information from common document types, such as the receipts or business cards or invoices. Document Intelligence uses OCR, or optical character recognition, as its foundational technology. And it uses that to extract the structure, relationships, the key values, entities, and other document-centric insights. When using Document Intelligence, you can create the standalone resource or use AI Services, which is a multi-service resource. Once you create the resources, you'll need to enable the service and add code to your application to consume the endpoint. You can first test the service in the Azure portal with some sample data and then view the JSON so that you can build your application accordingly. In this demonstration, you will see the Azure AI Document Intelligence service in action. So here we are in Azure AI Studio, and we're going to go to Vision and Document. And here are all the choices where we can perform AI with different types of documents. So we're going to go ahead and start with invoices. And we're going to take a look. We have some invoices in here that we can run the analysis on, and let's see what the results look like. So we run it on an invoice, and notice the visualization. So as we go down the list of the fields, you'll see them showing on the left. How those are created, you'll see here in the result, is from the JSON. All of those little dots and points in the JSON tell us where the bounding boxes go. So here's another good example of an invoice, and we get all of the information. So we have customer information in all the fields and the key value pairs essentially that we can parse from this. If we go over to our receipts, here's a nicely printed receipt, and it's going to tell us essentially where it comes from and what the different items are, where the city is, all of the information that's available on there. Again, we have the JSON result that tells us where those bounding boxes should be. And there's several different types of receipts. Here's a page receipt. This one is a little bit more like a form that you would expect it to be able to easily read. But here's a regular receipt that you might get from a store that might not be as readable. And again, the forms are all being outlined and shown to us as we go through. All right, so if we go back out and take a look at identifying documents. So identifying documents is you might get multiple documents sent in this case, potentially for ID purposes. So what it's going to do is it's going to do the normal document text extraction, but it's also going to determine what type of document it is. So here we've got the customs form. Here we have another form, and it's got the name of it. You can see it's actually putting in some of the native text that was on the form in place of where it is. There we go. And for our last one, here we have a West Virginia commercial driver's license. You'll see that shows up West Virginia commercial drivers. That's the content type. Then, of course, we have all of the individual fields that we have extracted from that as well. So that helps us categorize them as they go through. Now, the last one is going to be contracts. And so this is very powerful. So we have a single contract here, but we're going to run the analysis. And you're going to set apart some of the vital components at the top, and then each of the paragraphs is of the content via paragraph. And of course, the bounding boxes for where it appears is excellent, so we can then map to specific paragraphs. And that's been a great look at extracting information from forms. In this section, we will cover what is knowledge mining. We'll cover the three-step process to creating a knowledge store with Azure Search. Earlier in this session, I mentioned documents that contain a variety of company data in different forms. We have PDF files, Word documents, PowerPoint presentations, and many others. We can search for documents if we know the title, but what if we could search for documents by what they contain? What if we could extract insights from these documents and have those insights included in a search result? This is knowledge mining. Unlocking the data in our files, gaining insights, performing other AI skills on that data, and making it available as a search result or using it in research, reporting, and analysis. Azure AI Search connects to data in different ways. Unstructured data is supported through Azure Blob Storage, where you can upload Word documents or PDFs or other document types and ingest them into AI Search, where it will crack them and extract the text and images. It'll create JSON documents with the result and index the documents for retrieval. NoSQL is supported through Cosmos DB, Data Lake through table storage, and relational data supported through Azure SQL Database and SQL Server. A search index contains your searchable content. In Azure AI Search Solutions, you create a search index by moving data through the following indexing pipeline. So we start with a data source, the storage location or wherever your data is. So it could be PDFs, video files or images, or for Azure AI Search, you can also connect to files in Azure Storage, Azure SQL Server, or Cosmos DB. The indexer, it's going to automate the movement of the data from the source through the document cracking and enrichment to the indexing. An indexer automates that portion of the data ingestion and exports the file type to JSON in an action called JSON serialization. Document cracking is where the indexer opens the files and extracts the content. The enrichment is where the indexer moves data through AI enrichment, which implements Azure AI on your original data to extract for more information. AI enrichment is achieved by adding and combining skills in what's called a skill set. And that skill set defines the operations that extract and enrich the data to make it searchable. These AI skills can be built in, they can be built into the tools such as text translation, optical character recognition, or custom skills that you provide. Examples of AI enrichment include adding captions to a photo or evaluating text sentiment. AI-enriched content can be sent to a knowledge store, which persists the output from the AI enrichment pipeline into tables and blobs in Azure. So let's pause here for a moment. When we use skills that we don't have built into Azure AI Search, we're going to use our Azure AI Services multi-service account. And those work in an ecosystem, and then the output is going to go to a storage account. That's what we're saying there. So storage for the independent analysis or downstream processing is going to be wherever we choose, typically Azure Blob Storage. Now, push to index, the serialized JSON data populates the search index. That result is populated, which can then be explored through queries. So when a user makes a search query such as coffee, when we have a bunch of coffee data, it's going to look for that information in the search index, and the index has a structure like a table, which is an index schema. Think of it as a fast lookup. Typically, the search index schema contains fields, the field's data type, such as a type of a string, and then field attributes. So the field stores searchable text, and the field attributes allow for actions such as filtering and sorting. So below we see the action or the example of an index schema. In this demo, you will see Azure AI Search in action. In creating an index search, we're going to put some documents into a storage container to make it easy for our AI search to find it. So here I am in my Azure Data Search. I've created a container called coffee data. I can then go upload the information from my computer and I'll have all of my files here. Now my AI search will be able to connect to this data. So there's my data. I go back to my use your own data search, which is my AI search index, and I'm going to import this data. So I'm going to create a connection between my search index or my search resource and my data. So we're going to give this a name. We'll call it also coffee data. And then the next thing we need to do is get the connection string so that my search index can find the data that I want to use. So I'm going back to my data store, and I'm going to get the access key and the connection string, and I'm going to load that in. Go with coffee data, and there we go. It's inside of there. Now we're going to validate. So I've made a bunch of choices here. I'm going to allow Azure to go through and check my selections, make sure I haven't made any mistakes. All right, once that's done, we're going to add a skill. So the first thing we're going to do is we're going to go ahead and add some enrichments. So we're going to do some OCR, and then we're going to add a couple of skills here. So it's important to realize that the details of what you want to extract and any of the skills that you need to have, you have control over those at these levels here. So we're going to set a couple of contents to get some key phrases, some entities. We're going to do an image reference, and then we're going to connect, again, back to our data source. So we need to know where we're going to put our things. We're going to create a new container called knowledge store, and this is where the outputs are going to be sent from our index search. So the concept here is we're going to pull documents in, we're going to crack them open, we're going to extract images, we're going to get sentiment and some key analysis done for us, and then we need to write all of that data somewhere so that it can be retrieved later. So we're going to write it back to that same storage account, and now it knows how to do it. So we're going to go ahead and validate again. And now we want to filter everything that we're going to create. So we want to be able to filter through all of the choices that we made. So we're going to check off all these boxes, and we'll be able to go from there. And then we're going to go to the next step, which is to create an indexer. Once we make sure all of our selections here are accurate and correct, we'll move on to the next step. Now the indexer is, if you remember, we are going to use this to pull our data in. So this is the name of the tool. We're going to go ahead and rename this Coffee Indexer. And a Coffee Indexer is going to retrieve the documents and begin that process of cracking them open to create the index. The index will be the result of doing all of that work. So we're going to put some items in as configuration, and now we can see that it's being built. So what we have is it's in progress. We refresh it. Now it's ready to go. So our indexer has run, and now we can go do our data explorer. So if I type in coffee here, it's going to pull in all of the coffee data from our various coffee files that we uploaded. And let's try a couple different things in here. So I can switch over to the JSON view, and I can type in a more elaborate search process. Let's go ahead and do that now. There we go. And here I'm going to go ahead and paste in search for everything, asterisk, right? And the count is true. So now you see that our results are much longer. We don't need to go through all of those. Let's try something different. Let's go ahead and put location Chicago. Okay, so that's narrowed and filtered our results down to Chicago. All right, and we can see that there are some reviews and some other data in there. So let's try something with review. There we go. Let's do sentiment, negative, and here are all the negative reviews. So much shorter list, thankfully, for our coffee business. All right, the next thing we can do is we can take a look at the images that were pulled out of our documents, and here you see they are in separate folders, and we have all of our metadata about our images. And we have another set of a table where we have put all of our key phrases and our other IDs inside of there. So that has been a very quick look at using our documents and creating an index in Azure AI Search. In this session, we discussed document intelligence, data mining, and AI search. This concludes session 4. We're going to take another 10-minute break and come back with session 5, fundamentals of natural language processing, and I'll see you back in a bit. Welcome back from the break. This session is about working with generative AI. You may have heard of large language models or LLMs like ChatGPT and others. We will learn what makes LLMs different and how to harness them for your applications in Azure. So let's get started. This session is in 3 parts. We're going to talk about the fundamentals of generative AI, then we're going to do an introduction to Azure AI Studio, and explore responsible generative AI in AI Studio. In this module, we explore the way large language models enable AI applications and services to generate original content based on natural language input. We're going to learn how generative AI enables the creation of AI-powered copilots that can assist humans in creative tasks. By the end of this section, you'll be able to understand generative AI's place in the development of artificial intelligence and understand large language models and their role in intelligent applications. We'll also be able to describe how Azure OpenAI supports intelligent application creation and describe examples of copilots and good prompts. AI imitates human behavior by using machine learning to interact with the environments and execute tasks without explicit directions on what to output. Generative AI is a subset of AI in which an AI model creates original content in response to a natural language prompt. Generative AI applications take in natural language input as a prompt and return the appropriate responses in the following formats. Natural language generation. So to generate a natural language response, you might submit a prompt such as, give me 3 ideas for a healthy breakfast including peppers, or write a cover letter for my resume. Image generation. Some generative AI applications can interpret a natural language request and generate an appropriate image. For example, you might submit a request like, create an image of an elephant eating a plant-based burger, or create a logo for a florist business. Code generation. Some generative AI applications are designed to help software developers write code. For example, you could submit a request like, show me how to code a game of tic-tac-toe with Python, or write Python code to add 2 numbers together. While the mathematical principles behind language models can be complex, a basic understanding of the architecture used to implement them can help you gain a conceptual understanding of how they work. Today's large language models are based on transformer architecture, which builds on and extends some techniques that have been proven successful in modeling vocabularies to support NLP tasks, or natural language processing, particularly in the generating language. So transformer models are trained with large volumes of text. This enables them to represent the semantic relationship between words and use those relationships to predict probable sequences of text that make sense. So the transformer model with the large enough vocabulary can generate language responses that are tough to distinguish from human responses. In practice, the specific implementation of the architecture vary. For example, the bidirectional encoder representation from transformers, BERT, is a model developed by Google to support their search engine and uses only an encoder block to generate semantic vector representations of text, while the generative pre-trained transformer, or GPT model, developed by OpenAI uses a decoder block to generate sequences of natural language. While the complete explanation of every aspect of transformer models is beyond the scope of this module, an explanation of some of the key elements in transformer can help you get a sense for how they support generative AI. The encoder and decoder blocks in a transformer model include multiple layers that form the neural network for the model. We don't need to go into the details for all of these layers, but it's useful to consider one of the types of layers that is used in both blocks: attention layers. Attention is a technique used to examine the sequence of text tokens and try to quantify the strength of the relationship between them. So self-attention involves considering how other tokens around one token influence that token's meaning. In an encoder block, attention is used to examine each token in context and determine an appropriate encoding for its vector embedding. The vector values are based on the relationship between the token and the other tokens with which it frequently appears, or which appear in similar contexts. This contextualized approach means that the same word may have multiple embeddings depending on the context in which it is used. So for example, the bark of a tree means something different to I heard a dog bark. In a decoder block, attention layers are used to predict the next token in a sequence. For each token generated, the model has an attention layer that considers the sequence of tokens up to that point. The model considers which of the tokens are the most influential when considering what the next token should be. So remember that the attention layer is working with numeric vector representations of the tokens, not the actual text. In a decoder, the process starts with a sequence of token embeddings representing the text to be completed. During training, the goal is to predict the vector for the final token in the sequence based on the preceding tokens. The attention layer assigns a numeric weight to each token in that sequence, and it uses the value to perform a calculation on the weighted vectors that it produces an attention score. That can be used to calculate its possible vector for the next token. So in practice, a technique called multi-head attention uses different elements of the embeddings to calculate multiple attention scores. Then a neural network is used to evaluate all possible tokens to determine the most probable token which will continue the sequence. The process continues iteratively for each token in the sequence, with the output sequences so far being used regressively as the input for the next iteration, essentially building the output one token at a time. The first step in training a transformer model is to decompose the training text into tokens. In other words, identify each unique text value. For the sake of simplicity, you can think of each distinct word in the training text as a token, though tokens can be made for partial words or a combination of words and punctuation. With the sufficiently large set of text on which to train, a vocabulary of many thousands of tokens can be compiled. As you continue to train the model, each new token in the training text is added to the vocabulary with the appropriate token IDs. I is 1, herd is 2, A is 3, dog is 4. With a sufficiently large set of training text, a vocabulary of many thousands of tokens can be compiled. To create a vocabulary that encapsulates semantic relationships between the tokens, we define contextual vectors known as embeddings. Vectors are multi-valued numeric representations of information. For example, 10, 3, 1, in which each numeric element represents a particular attribute of the information. For language tokens, each element of a token's vector represents some semantic attribute of the token. The specific categories for the elements of the vectors in a language model are determined during training based on how commonly words are used together or in similar contexts. Vectors represent lines in multidimensional space describing direction, distance along multiple axes. You can impress your mathematical friends by calling these amplitude and magnitude. It can be useful to think of the elements in an embedding vector for a token as representing steps along a path in multidimensional space. For example, a vector with 3 elements representing a path in 3-dimensional space in which the element values indicate the units traveling forward, backward, left, right, up, or down. Overall, the vector describes the direction and distance of the path from origin to the end. The elements of the tokens in the embeddings space each represent some semantic attribute of the token, so that semantically similar tokens should result in vectors that have a similar orientation, or in other words, they point in the same direction. A technique called cosine similarity is used to determine if two vectors have similar directions, regardless of the distance, and therefore represent semantically linked words. For example, the embedding vectors for dog and puppy describe a path along an almost identical direction, which is also very similar to the direction for cat. But the embedding vector for skateboard will have a different journey, and it describes that journey in its vector, or in its embedding. Note, the example here shows a simple model in which each embedding has only 3 dimensions. Real language models have many more dimensions. There are multiple ways you can calculate appropriate embeddings for a given set of tokens, including language modeling algorithms like word2vec or encoder block in a transformer model. The encoder and decoder blocks in a transformer model include multiple layers that form the neural network for the model. The encoder and decoder blocks in a transformer model include multiple layers that form the neural network for the model. And we don't need to go into the detail for all of these layers, but it's useful to consider one of the types of layers that it's used in both blocks, the attention layers. Attention is a technique used to examine a sequence of text tokens and to try to quantify the strength of the relationship between them. So self-attention involves considering how other tokens around one token influence that token's meaning. In an encoder block, attention is used to examine each token in context and determine an appropriate encoding for its vector embedding. The vector values are based on the relationships between the token and the other tokens with which it frequently appears. This contextualized approach means that the same word might have multiple embeddings, and depending on the context in which it's used, for example, the bark of a tree means something different to I heard a dog bark. In the decoder block, attention layers are used to predict the next token in a sequence. So for each token generated, the model has an attention layer that considers the sequence of tokens up to that point. The model considers which of the tokens are the most influential when considering what the next token should be. So remember that the attention layer is working with numeric vector representations of the tokens, not the actual text. In a decoder, the process starts with a sequence of token embeddings representing the text to be completed. During training, the goal is to predict the vector for the final token in the sequence based on the preceding tokens. The attention layer assigns a numeric weight to each token for that sequence so far. So it uses that value to perform a calculation on the weighted vectors that produce an attention score that can then be used to calculate a possible vector for the next token. In practice, a technique called multi-head attention uses different elements of the embeddings to calculate multiple attention scores. A neural network is then used to evaluate all the possible tokens to determine the most probable token with which to continue the sequence. The process continues iteratively for each token in the sequence, with the output sequence so far being used regressively as the input for the next iteration, essentially building the output one token at a time. The following animation shows a simplified representation of how this works. In reality, the calculations performed by the attention layer are more complex, but the principles can be simplified as shown. A sequence of token embeddings is fed into the attention layer. Each token is represented as a vector of numeric values, and the goal in the decoder is to predict the next token in the sequence, which will also be a vector that aligns to an embedding in the model's vocabulary. The attention layer evaluates the sequence so far and then assigns weights to each token to represent their relative influence on the next token. The weights can be used to compute a new vector for the next token with an attention score. Multi-head attention uses different elements in the embeddings to calculate multiple alternative tokens. A fully connected neural network uses the scores in the calculated vectors to predict the most probable token from the entire vocabulary. The predicted output is appended to the sequence so far, which is used as the input for the next iteration. During training, the actual sequence of tokens is known. We just mask the ones that come later in the sequence than the token position currently being considered. As in any neural network, the predicted values for the token vector is compared to the actual value of the next vector in the sequence, and the loss is calculated. The weights are then incrementally adjusted to reduce the loss and improve the model, and when used for inferencing or predicting a new sequence of tokens, the trained attention layer applies weights to the predicted the most probable tokens in the model's vocabulary, and that is semantically aligned to the sequence so far. What this means is that a transformer model such as GPT-4, the model behind ChatGPT and Bing, is designed to take the next input called a prompt and generate a syntactically correct output called a completion. In effect, the magic of the model is that it can string a coherent sentence together. This ability doesn't imply any knowledge or intelligence on the part of the model, just a large vocabulary and the ability to generate meaningful sequences of words. What makes a large language model like GPT-4 so powerful is the sheer volume of data with which it has been trained. So public and licensed data from the internet is used. The complexity of the network and its ability for the model to generate completions is based on the relationships between words in the vocabulary on which the model was trained, often generating output indistinguishable from a human response to the same prompt. A diagram that shows how the attention technique helps the large language models identify the next word in the sequence. The image shows words and their positioning in the encoding layer coordinates. Organizations and developers can train their own language models from scratch, but in most cases, it's more practical to use an existing foundation model and optionally fine-tune it with your own training data. There are many sources of models that you can use. On Microsoft Azure, the Azure OpenAI service includes a curated set of models from OpenAI hosted in Azure. This offers the benefit of cutting-edge language models like the Generative Pre-trained Transformer, or GPT, collection of models on which ChatGPT and Microsoft's own generative AI services are based, as well as the DALL-E model for image generation. Using these models from the Azure OpenAI service means that you also get the benefit of a secure, scalable Azure cloud platform in which the models are hosted. The Azure OpenAI models are included in the Model Catalog, a curated source of models for data scientists and developers using Azure AI Studio and Azure Machine Learning. In addition to the Azure OpenAI models, the Model Catalog includes the latest open source models from Microsoft and multiple partners including OpenAI, Hugging Face, Mistral, Meta, and others. There are many language models available that you can use to power generative AI applications. In general, language models can be considered in two categories: large language models, or LLMs, and small language models, or SLMs. Large language models are trained with vast quantities of text that represent a wide range of general subject matter, typically by sourcing data from the internet and other generally available publications. When trained, large language models have many billions or even trillions of parameters. These are weights that can be applied to vector embeddings to calculate predicted token sequences, as we've discussed, enabling them to exhibit comprehensive language generation capabilities in a wide range of conversational contexts. However, their large size can impact the performance and make it difficult to deploy locally on devices and computers. Additionally, if you want to fine-tune the model with your own additional data to customize its conversational subject expertise, the process can be time-consuming and expensive in terms of the compute power required to perform the additional training. Conversely, SLMs, or small language models, are trained with smaller, more subject-focused data sets and typically have fewer parameters than the LLMs. This focused vocabulary makes them very effective in specific conversational topics, but less effective in more general language generation. The smaller size of SLMs can provide more options for deployment, including local deployment to devices and on-premises computers. And it makes them faster and easier to fine-tune. Copilots are generative AI assistants that are integrated into applications, often as chat interfaces. They provide contextualized support for common tasks in those applications. Business users can use copilots to boost their productivity and creativity with AI-generated content and the automation of tasks. Developers can extend copilots by creating plugins that integrate them into business processes and data, or even create custom copilots to build generative AI capabilities into apps and services. The slide here shows Microsoft Copilot for Microsoft 365, which enables you to summon a chat assistant when you are working in Windows or a Microsoft 365 application such as Outlook or Word. Using a copilot like this can help you get more things done in less time. On the next few slides, we'll explore some of the ways in which Microsoft Copilot has been integrated into apps to provide contextual assistance. There are 3 levels of Copilot adoption in an organization. You can use off-the-shelf copilots like Microsoft Copilot for Microsoft 365 to empower users and increase their productivity. You can extend Copilot to support custom business processes or tasks using your own data to control how Copilot responds to your prompts in your organization. Or you can build custom copilots to integrate generative AI into business apps or to create unique experiences for your customers. You can use Microsoft Copilot to browse the web more effectively. The Microsoft Copilot app at copilot.microsoft.com provides Microsoft Copilot's home on the web. You can go here and ask questions and generate content such as text and images. Signing in with a work or school account enables you to use Copilot in the context of your organization's data and services or your own. It enables you to get the assistance without internal resources and information. Microsoft Copilot for Microsoft 365 integrates Copilot into the productivity applications that information workers use every day. For example, you can use Copilot in Microsoft Word to generate a new document based on a natural language prompt, and then refine, summarize, and improve the document with a few prompts. You can use Copilot in Microsoft PowerPoint to create a whole presentation based on the contents of a document or an email, and then add graphics, reformat slides, and otherwise improve your presentation. In Microsoft Outlook, Copilot can help you summarize your emails, check your schedule, even find relevant emails and documents to prepare for meetings. Microsoft Dynamics 365 is a suite of business tools that helps users in specific roles perform business processes. Copilot for Dynamics 365 provides contextualized assistance to those tools and helps users be more efficient and effective. For example, sales professionals can use Copilot to quickly find relevant customer and industry information by integrating with the company's customer relations management or CRM database and beyond. This can enable an account manager to quickly review and qualify a lead, generate a proposal, and then set up a customer engagement to close the deal. Customer service agents can use Copilot in Dynamics 365 Customer Service to analyze support tickets, research similar issues, find resolutions, and communicate to the users with only a few clicks and prompts. Data analysts must work with code and visualization tools to analyze data and report insights. In Microsoft Fabric, Copilot enables an analyst to automatically generate the code that they need to analyze, manipulate, and visualize data in Spark notebooks. And when creating Power BI reports, Copilot can analyze your data and then suggest and create the appropriate data visualizations from that. Copilot for Azure is integrated into Azure Portal and can assist infrastructure administrators as they work with Azure Cloud Services. Microsoft Copilot for Security helps security professionals as they assess, mitigate, and respond to security threats. GitHub is the world's most popular place for developers to manage their code and develop applications. GitHub Copilot helps developers maximize productivity by analyzing and explaining their code, adding code documentation, generating code based on natural language prompts, refactoring, optimizing code, generating test cases for code for existing functions, and integrating into developer tools like Microsoft Visual Studio Code, which means you can take it anywhere, and it does so much more. While some Copilots provide buttons and other visual tools to interact with language models, you will often use a Copilot by typing or speaking a natural language prompt. The specific prompt that will yield the most effective results can vary depending on the specific task you're trying to accomplish, the Copilot being used, and the language model it's being supported by. However, there are some common prompting techniques that you can apply to get the best out of your Copilot. You start with a specific goal in mind. What is it you want the Copilot to do? And you be very explicit here. You want to provide a source to ground your response in. So a specific scope of information. This will help ensure the response is based on real data. And add context. Context is key. This can help the language model craft an appropriate response. Then set clear expectations for the response. Be very explicit about the format and scope of the expected results. Iterate based on your past prompts and responses to refine your output. In most cases, a Copilot does not just send your prompt as is to the language model. Usually your prompt is augmented with a system message that sets conditions and constraints for the language model behavior. And the conversation history for the current session can also be included if you don't start a new session. And this enables you to refine your response iteratively while maintaining the context of the conversation. That current prompt, potentially optimized by the Copilot to reword it and appropriate it for the model or to add additional grounding to the data, to the scope of the response, is then sent to the model. The success you have with Copilots and generative AI in general depends largely on how well you craft your prompts. The importance of using good prompts has led to new discipline in prompting engineering. And let's pause here for a second. And I want to stress, don't shy away from longer prompts. We see a lot of examples that are short, but when you add a lot of context and you add all those pieces together, don't be afraid to have a long prompt to work with, and you're going to get the best results if you do that. If your organization makes the decision to customize Microsoft Copilot or develop custom Copilots, Microsoft provides two tools that you can use. Copilot Studio is designed to work with low-code and development scenarios in which a technically proficient business user or developer can create conversational AI experiences. The resulting Copilot is a fully managed software as a service solution hosted in your Microsoft 365 environment and delivered through chat channels like Microsoft Teams. With Copilot Studio, the infrastructure considerations and model deployment details are taken care of for you, making it easier to focus on creating an effective solution. Azure AI Studio is a platform as a service development portal for professional software developers that gives you full control over the language model you want to use, including the capability to fine-tune the model with your own data. You can define prompt flows that orchestrate conversation flow and integrate your own data augmentation and prompt engineering logic, and you can deploy the resulting Copilot service in the cloud and consume it from custom-developed applications and services. Let's look at generative AI with Microsoft Copilot. Here I am in the browser, and I have my OneDrive open, and I'm signed in with my personal Microsoft account, and I have this document, this business ideas document, and it's in my OneDrive. And this is important because I'm in the browser. Then I opened up Copilot in the browser, and the web experience here, it's going to be the same for everyone, right? So I've got the Copilot open, and whatever web page I have open, it can read. So let's ask it, what is this document? All right, so what is it about? It's going to go ahead and semantically understand. So we know it's going to take all of this information, send it to the model, and say, what is this document about, and send it back. So now I want to find out, well, it's about a business idea. How do I open up a business in New York City? That's what we want to do, right? So here's all of the steps that I would have to take. This is all relevant to my document, and this conversation is ongoing. So now I want a new name for my business, and I'm going to go with Pure Clean New York City. So let's go with that. And now I want a business plan. So I've gotten ideas, all just in a matter of minutes here. I know how to open up a business. I've got a new name for my product, and I've got a business plan that I can now add to my document. And of course, I would keep refining this. These are all first drafts when we get these back from Copilot. We want to go through and do our fact checking here. Now, the next step. What is the next step? We can take the power of this AI, and here I am logged in with my work account. This is Copilot for Microsoft 365. You can see I have my labels, but what I'm doing here is I'm prompting against my own documents, and I'm going to call 3 documents, and I want a comprehensive strategic analysis for my Contoso Learn, and put these separate items in there. So an executive summary and an account and all of that. So look at this. There's my new document. So I had 3 documents that are 6, 7, 8 pages each, and now I've got a new summary document that's 3 pages long. And again, it's a first draft. All right, so what else can I do with this? Well, if I go to PowerPoint, I can now call this document from PowerPoint. And I've put the URL in it, and I basically say, hey, you know what, create a PowerPoint from this document. And it's going to go semantically read my summary document with all of the steps. You can see it has all of the executive summaries, the app overview, market research, and it's going to semantically understand how to build an appropriate PowerPoint and even give me speaker notes. And that's been a quick tour of Microsoft Copilot and Microsoft Copilot M365. This section we will discuss Azure AI Studio and how it provides a single solution for AI development with multiple Azure AI services. An Azure AI resource defines a collaborative workspace for AI development with Azure AI Studio, and an Azure AI project provides a shared collection of assets and code for a particular AI solution. Azure AI Studio is a PaaS, or Platform as a Service, development portal for professional software developers that gives you full control over the language model you want to use, including the capability to fine-tune the model with your own data. The growth of the use of artificial intelligence, AI in general, and generative AI in particular, means that developers are increasingly required to create comprehensive AI solutions. These solutions need to combine machine learning models, AI services, prompt engineering solutions, and custom code. Microsoft Azure provides multiple services that you can use to create AI solutions, but until now, developers have needed to work with multiple tools and web portals in a single project. Azure AI Studio brings together capabilities from Azure Machine Learning, Azure OpenAI Service, and other Azure AI-related services into a single centralized workspace within which developers can collaborate with data scientists and others to build AI solutions. Azure OpenAI Service is Microsoft's cloud solution for deploying, customizing, and hosting language models. Azure Machine Learning is Microsoft's solution for training and deploying machine learning models and managing machine learning operations, or MLOps. Azure AI Services encompasses Microsoft's cloud solutions for creating cutting-edge, market-ready, and responsible applications with pre-built and customizable APIs and models. Azure AI Studio is a web portal that brings together multiple Azure AI-related services into a single, unified development environment. Specifically, Azure AI Studio combines the model catalog and prompt flow development capabilities of Azure Machine Learning Service and the generative AI model deployment, testing, and custom data integration capabilities of Azure OpenAI Service, and integration with Azure AI services for speech, vision, language, document intelligence, and content safety. AI Hubs in Azure AI Studio are top-level resources that provide a centralized setup and management for AI projects. offering features like data upload, artifact storage, connections to Azure services, base model endpoints, compute resources, and governance controls. You can perform the following tasks in the AI Hub level. You can create and manage connections to resources such as data stores, GitHub, Azure AI search indexes, and others. You can create and manage compute instances on which to run experiments, prompt flows, and custom code. You can set up security by creating members and assigning them to specific roles, and set up governance by defining policies to manage behavior, such as automatic compute shutdown. Projects are organizational containers within a hub that allow for AI customization and orchestration. They help your organization work, save state across different tools like prompt flow, and collaborate with others. Projects can use shared resources from the AI Hub and have dedicated storage containers for uploading files and sharing with project members. With an AI project, you can deploy foundation models from the model catalog and test the models in the chat playground, augment prompts by connecting to custom data sources and connections, and build copilots with prompt flow, evaluate model and application performance by using built-in and custom metrics, and manage the deployment of your models and apps. With role-based access control, or RBAC, you can assign roles to users and give them access on the AI Hub or the project level. Things we can do in Azure AI Studios are create and manage AI projects. So Azure AI Studio provides a centralized hub for all your AI projects, allowing you to manage resources, collaborate with the team members, and streamline your workflow. You can develop generative AI applications. If your goal is to develop an application that can generate content or build your own prompt flow, Azure AI Studio's generative AI capabilities are essential. You can explore available AI models. So experiment with various AI models from OpenAI, Microsoft, Hugging Face, and more in Azure AI Studio's model catalog. You can leverage retrieval augmented generation, or RAG. For projects that require combining the power of retrieval and generation, Azure AI Studio's RAG features enhance the quality and relevance of the generated content. You can monitor and evaluate AI models. So Azure AI Studio provides robust tools for evaluation and monitoring of your prompt flows and AI models, ensuring they meet the desired performance metrics. You can also integrate with Azure services. When your AI applications need to work seamlessly with other Azure services, Azure AI Studio offers easy integration, making it a versatile choice for your complex, multifaceted projects. You can build responsibly. Azure AI Studio emphasizes responsible use of AI, providing guidance and tools to ensure that your applications adhere to ethical standards and best practices. Prompt flow is a feature within Azure AI Studio that allows you to author flows. Flows are executable workflows integrating with language models, and your prompt flow in Azure AI Services is a development tool designed to streamline the entire lifecycle of an AI application powered by the large language models. It simplifies the process of prototyping, experimenting, iterating, and deploying AI applications. Here are some key features. Visualized graphs. You can orchestrate executable flows with large language models, prompts, and Python tools through a visual interface. Prompt variants. Create and compare multiple prompt variants to refine your AI models. And you have evaluation tools. Built-in evaluation flows help assess the quality and effectiveness of your prompts and flows. You can also share and iterate on flows easily with team collaboration. And the prompt flow, it should be noted, is available as an open source project on GitHub and as a feature within Azure AI Studio and Azure Machine Learning Studio. A flow is an executable instruction set that can implement the AI logic. Flows can be created or run via multiple tools like a pre-built canvas, LangChain, etc. Iterations of a flow can be saved as assets. Once deployed, a flow becomes an API. Not all flows are prompt flows. Rather, prompt flow is one way to create a flow. The model catalog in Azure AI Studio is the hub to discover and use a wide range of models that enable you to build generative AI applications. The model catalog features hundreds of models across model providers such as Azure OpenAI Service, Mistral, Meta, Cohere, NVIDIA, Hugging Face, including models trained by Microsoft. Models from providers other than Microsoft are non-Microsoft products as defined in Microsoft's product terms and subject to the terms provided with the model. As discussed in the earlier section, generative AI models are excellent at understanding and creating natural language. They can write code from natural language prompts. They can edit and create images based on the model type. The model that works with images is called DALL-E, which supports image creation, image editing, and image variations creation. In this demo, you'll see Azure AI Studio's capabilities in action. So here we are in Azure AI Studio. And as you can see, we have all of our Azure AI services right here. And what I want to do is I want to work with my Azure OpenAI. And if I go to my OpenAI, I can see I have some legacy services that I can see there, but I'm going to create a new service inside of Azure Studio. You can see when I go there, there isn't anything there. So we're going to go back and I'm going to create a new project. So part of Azure AI Studio is we have the projects and the hubs. And so here I'm going to create a new project, and with it, we're going to get a hub. And that hub's going to allow us to then share and invite people and collaborate with the results of creating this project. So give that just a minute to create. All right, now that we're there, we can go through and take a look at the different models and the different things that we can create. What I want to do is I want to build or deploy a new model. In this case, I'm going to choose a GPT model. I want GPT-4o. So I'm going to go deploy model. I'm going to choose 4o, and then I'm going to go ahead and fill out all of my stuff here. So here I'm lowering the token amount. Your tokens are based on the region, and we don't want to overuse. We want to definitely dial that number in specifically. All right, now I can see the details about my GPT-4o deployment, and I can go to the chat playground. So really quickly, we're just going to ask it a question. We just did this. So what's going to happen here is it won't necessarily be available immediately. And as you see, it wasn't available. So let's try it again. Give it a minute to, there we go. Artificial intelligence is, so what is it? Maybe we can even do things like ask it to do that in another language. And that has been a quick tour of Azure AI Studio and Azure OpenAI. This section has two parts: plan a responsible AI generative AI solution and operate a responsible generative AI solution. The Microsoft guidance for responsible generative AI is designed to be practical and actionable. It defines a four-stage process to develop and implement a plan for responsible AI when using generative AI models. The four stages in the process are: identify potential harms that are relevant to your planned solution. Measure the presence of these harms in the outputs generated by your solution. Mitigate the harms at multiple layers in the solution to minimize their presence and impact, and ensure transparent communication about potential risks to users. Operate the solution responsibly by defining and following a deployment and operational readiness plan. These stages correspond closely to the functions in the NIST AI Risk Management Framework. The remainder of this learning objective discusses each of these stages in detail, providing suggestions for actions you can take to implement a successful and responsible generative AI solution. Azure Content Safety has several key features such as prompt shields, scans for the risk of the user input attacks on the language models, groundedness detection, detects if the text responds are grounded in a user's source content, protected material detection, which scans for known copyrighted content, custom categories, and then also defining custom categories for any of these new and emerging patterns. Let's look at Azure AI content filters. Here I am in the chat playground, and I'm going to open up my content filter section. So again, we're in the Azure OpenAI inside of Azure AI Studio. I open up the content filters, and this is where I can set the thresholds for incoming and outgoing text. So if I am on high threshold, that means I'm going to allow more. And if I'm on low threshold, that means I'm going to allow less information through. So I'll leave that one set to low. And I also have my jailbreak attack, which is an attempt to get the model to do something it's been trained to not do. And then we have prompt shields for indirect attacks. In this case, we're just going to annotate if something happens. Now on the return from the model, I can do the same. So if the model decides to return something that's going to be something I don't want my customers to see or my employees to see, I can allow less or be less tolerant, or I can allow more and be more. It's important to know that you can have all of these filters removed from your model. If you have a need, you just ask Microsoft and they'll remove them for you. So here what we're going to do is we're selecting our model, and once we're done and we create our filter, it's going to be applied directly to that 4o model. You can do this later as well, but that is a quick walkthrough of how to set the thresholds for your content filters and have custom content filters on your different models. In this session, we talked about generative AI and what makes it different from other AI models. We talked about the different ways to work with generative AI in Azure and how to be responsible and the ways that we can protect and monitor our services. This concludes our session, and thank you so much for attending Microsoft 365 Virtual Training Day on AI Fundamentals. Remember, there are many ways to continue your learning journey, such as at Microsoft Learn or aka.ms/learn, where we offer self-paced learning options. Happy studying.